Hey guys, today we're going to go over factoring. So what is factoring? In lower level maths, you've probably run into it. It's when you see the same common factor present in multiple terms at once, and then you rewrite the equation to have the common factor outside brackets being multiplied in. It's like reverse distribution. You're finding out what number goes outside the brackets that make the equation equal. I think the easiest way to demonstrate what factoring is to just show it. So let's say we have the equation 3x minus 3 equals y. You might notice that there is a 3 coefficient in both terms. Let me change my pen color real quick. Yeah, we have 3x and we have 3 times 1. What we can do now is we can divide both terms by 3 and then put the quotient into brackets. Then we'll multiply the whole bracket by 3 to undo our original division. So these 3's are going to come out of the equation. They're going to end up here. And then we're going to have a new set of stuff inside these brackets. So what this will look like, we bring out the 3. 3x divided by 3 is just x. And 3 divided by 3 is just 1. So we now have 3 times x plus minus 1 equals y. If we want to distribute this back in, we have 3x minus 3 equals y. Same thing. So it's exactly like reverse distribution. That is kind of the essence of factoring. It's essentially rewriting an expression as the product of 2 or more polynomials instead of 1. And you do this by finding out what could possibly be separated from both of the terms. So let's move on to another example. When you factor, you're always going to want to identify common factors in each term of the expression. Sometimes you end up with terms like this, where it's 3x plus 9y plus 12z. If we take a look at this, we can see immediately that there is a common factor of 3 in all 3 of these terms. This divided by 3 is just x, this divided by 3 is just 3y, this divided by 3 is just 4z. So if we were to divide it by 3, this would be our quotient. And yeah, let's go ahead and divide by 3. We're going to factor out the 3. So we put the 3 on the outside of the brackets. And then now we just put the quotient inside of the brackets. So in this case, we have 1x plus 3y plus 4z. If we distribute it back in, you can see that we've already divided all these by 3. We distribute it back in, we get 3x plus 9y plus 12z. Fairly simple. Okay, since there are no other common factors in this polynomial right here inside of the brackets, we can say that this is fully factored. Sometimes you can actually factor out multiple things at once, but that's just probably because you missed another common factor when you were doing it the first time. But if you do that, just multiply it by the outside. So in addition to factoring out constants, we can also factor out variables. Let's take the expression x squared plus x. We can immediately identify a common factor x in both terms. X squared is just x times x, and x is just x times 1. We know that there's a common factor here, and so that we know that we can immediately factor out one x term. Dividing both sides by x, we get x. This turns into 1. And then now we have x times x plus 1. Let's look at another example. 3x squared y plus 3xy. So this is what I was talking about before. I'm going to show you 2 ways to do this. You could do it in 2 steps, or you could do it in 1. It just depends how good you are at determining what common factors are in each polynomial. So in this case, let's just split this up into parts. I'm going to teach you the 1-step method first. So now we have 3, we have x, and we have y. Here we have 3, we have x, and we have y. So the simple way to do it is to just figure out, oh, which terms are common across all of these. We have a 3 term, an x term, and a y term. So we can immediately just factor out 3xy from each of the equations, because each of these terms has a factor of 3xy in them. This is what we're doing when we're breaking it down and factorizing it. We're just finding out what is the common factor, essentially. So now that we've done that, we can just divide this by 3xy. We get x plus 1. And there's our factor term. Now, another way you could do it is you could do it one step at a time. So you could do, let's just say, I'm going to erase all this marking right here. Sorry, I'm not used to this tablet. Okay. You could do the 3 first. So now we're going to have 3 times x squared y plus xy. There's the constant term. Now we can move on to the variable terms. We can see that there's a y present in both. So then we're going to factor out the y. Again, divide the inside, multiply the outside. 3y times x squared plus x. Then we find another common term, which is going to be the x, because both x will go into both of the terms inside of the bracket. So we're going to divide the inside, multiply the outside. 3yx times x plus 1. And there's our final answer. Notice how this and this are the same thing. All right. A little bit of a bonus. Even if there are no common factors in a expression, if you want to isolate an x term, or for whatever reason, you can also factor out things that from constants or variables that don't necessarily present as a perfect match. So in this case, I want to factor out the 3 to isolate the x. But we also got a 1 term. So what we have to do is we need to, again, divide the inside by 3. 3x plus, since we're dividing the inside by 3, we need to divide this term and we need to divide this term. That term is going to end up being 1 over 3. You can see that this is true because if we want to multiply it back in, we get 3x plus 1. Well, actually, no, we don't get 3x plus 1. We get 3x plus 3 times 1 over 3, which is just equals to 1. So we're just going to write that as 1. This will also work for other expressions like, let's say, 5x plus 2, where we can factor out the 5, and then we'll make x plus 2 over 5. If we want to multiply this back in, we just get 5x plus 2 again. This even could work for variables. So let's just say we want to completely isolate x. And I don't know of any equation that's going to require this, but it helps to build on the concept. Let's say we have 5y plus 3, 5yx plus 3, sorry. If we want to factor this and isolate x, we could just do 5y times x plus 3 over 5y. And again, when we want to multiply this back in, we're just going to end up with this expression. If you want to do that, I leave it up to you. But we're just going to move on. Now let's take a look at the more common type of factoring, which is going to be factoring quadratic trinomials. This and factoring cubic trinomials are going to be very common in Pre-Calc 11. Actually, more this, not so much cubic. Cubic's more Pre-Calc 12. But yeah, so let's go into what a quadratic equation is. A quadratic trinomial takes the form ax squared plus bx plus c equals 0. Actually, no, it doesn't. This is a quadratic equation. It's slightly different, but this will help you solve for when y equals 0 later on. But a quadratic trinomial only takes the form ax squared plus bx plus c. So right now I'm going to show an easy way to factor these. I'm going to show an expansion on the method and an application of the quadratic formula so that you can determine roots. Quadratic formula stuff is with the quadratic trinomial equal to 0, but I'll get into that more later. So before we get into factoring, I want to reference one of the example problems we did before. Let's take a look at this one on screen right now. Notice how this quadratic equation can be factored into two separate polynomial terms, each of them containing an x. Most of these quadratic equations or trinomials can be factored into stuff resembling this. Some cannot. Again, we'll get into that later, but right now we're going to focus on the ones that can. Let's start with talking about a quadratic trinomial without an a term. So an a term is, again, if your quadratic trinomial has the shape ax squared plus bx plus c, a quadratic trinomial without an a term is essentially the same as saying where a is 1. 1x squared plus bx plus c. These are the easiest type of quadratic trinomials to factor, and it's usually pretty easy to figure out if it's even factorable or not. So when we see a quadratic trinomial, we already know 3 things right off the bat. 1. If it is factorable, the polynomials that make up, let's just say, call it x plus d, x plus f. We know that the polynomials that make up the quadratic are both going to have a constant term, even if the constant term is 0. So the first part of FOIL, f, we have the x term times the x term. Sometimes this might have a coefficient, which will create an ax term, but in this case, we're just going to have an x term. This is going to create the x squared term of the quadratic, and there is usually only 1. Then the o and the I. These represent the inner steps, so x times f and d times x. So that's going to create the x terms. So we have x squared plus dx plus fx. And the last part is what's really important. See this last term, the c right here? This is created by the d times f. So in this case, the df is the only thing that is responsible for your c term. And that means if you can figure out the stuff that can get multiplied to make your c term, then you're going to have a lot easier time figuring out what your d term and your f term is. So, number 2. In the FOIL method, we create dx and fx terms in the o and I steps, like we mentioned before. And these two will add up to create the bx term. I really regret using d and f as variables, but you know what? It's fine. We're going to keep going like this. Just know that this is not a function, and this is not a derivative. These are just constants. All right. So again, c is going to be equal to df. b is going to be equal to d plus f. With this knowledge, we can solve for the roots of any quadratic trinomial if it is possible. And I'm going to show you how to do that now. So let's take the example x squared plus 4x plus 3. We know that this quadratic trinomial is going to break down into the form x plus d, x plus f. We also know df is equal to 3. And we know d plus f is going to be equal to 4. Since our b term is 4, our c term is 3, df equals c, and d plus f equals b. Now, armed with these 3 pieces of information, we can ask ourselves, what combinations of d and f both multiply together to make 3, and also add to make 4? In this case, the answer is quite obvious. The only whole numbers that can multiply together to make 3 is 1 and 3. And these guys also add to make 4. Therefore, we know that there's going to be one term that's a 3, and there's going to be one term that's a 1. Therefore, our expression is going to be x plus 1 times x plus 3, or x plus 3 times x plus 1. It really doesn't matter. It's a times b, times a. It's the same thing. All right. That equation was really obvious, but let's get into another one. So we're going to try this one this time. X squared plus 7x plus 12. Again, we know that our d and our f terms will make 12. D plus f is going to make 7. This time, though, there is a lot of stuff that can be multiplied together to make 12. So let's list them out. 12. The pairs that can make 12 are as follows. 1 times 12, 2 times 6, 3 times 4, 4 times 3, 6 times 2, 12 times 1. And given that the top half is literally the same thing as the bottom half, I'm just going to get rid of this real quick. Because 2 times 6 is just 6 times 2, and it really doesn't matter. So we're left with 3 choices. Now let's use our second piece of information. We know that our 2 constant terms have to add to make 7. Let's add up each one of the possibilities and see what they make. So if d and f are 1 and 12, b would have to be 13. Is b 13? No, this one's gone. If d and f are 2 and 6, b would have to be 8. Is b 8? No, b is 7. So this one's also gone. And now we're left with 3 and 4. If 3 and 4 are d and f, then b would have to make 7. Is b 7? Yes, it is. So we know that our d and f term are going to be 3 and 4. Therefore, we can factor this expression into x plus 3, x plus 4. And if you want, you can FOIL this out to check. It will create this expression. You know what? I'm just going to do it right now. X squared plus 3x plus 4x plus 12. Combine like terms. Now we have plus 7x. And boom, we have our original expression. And this step is literally just me foiling it out. Okay. Occasionally, you're going to have negatives involved in your factoring. So let's take a look at another example. We have x squared plus 4x minus 12. Okay, so the same rules remain true. df equals c equals negative 12. d plus f equals b equals 4. Let's do the exact same thing and go ahead and lay out all the possible combinations. So since this is going to be negative, and it's 2 numbers multiplying to make negative, you know that it's going to be 1 positive and 1 negative number. So let's just list them out. Negative 1 times 12, negative 2 by 6, negative 3 by 4, negative 4 by 3, negative 6 by 2, and negative 12 by 1. Cool. All right, these are all the possible combinations of d and f that would satisfy the c term. Now let's check which one's going to satisfy the b term. So if we're going to add this up, we get 11. That's not b. Can't be that. We add these up, we get 4. Oh, could be. Add these up, we get 1. Yeah, no. Add these up, negative 1. Nope. Negative 4, definitely not. And negative 11, definitely not. So the only one that works is negative 2 and 6, because this is the only pair of d and f that would add up to 4 and multiply into 12. So our polynomial expression is going to be x plus 6 times x minus 2. As you practice doing these, and I highly recommend practicing them, and I mean like maybe 10, 20 questions a day for, a week, you will be able to do these mentally incredibly quickly. Unfortunately, it is a thing that comes with practice. So, it's not that painful. Eventually, you will find yourself skipping steps, and that's when, you've kind of got the hang of it. We're going to FOIL this out just to check our answer. Oh yeah, there's another thing. With a factoring question, just FOIL out your factor if you're not sure about your answer. And do our answers match up? Yes, they do. Cool, we did this right. So sometimes we have quadratic expressions with a coefficient for the x squared term, also known as the a term. So these are usually pretty tough to factor, but there's a method called the AC method, which is fairly intuitive. So let's say we have a quadratic expression 2x squared plus 5x plus 2. In this case, a is 2, b is 5, c is 2. The AC method of factoring goes as follows. So you're going to take your a term, and you're going to multiply into your c term to create a new polynomial expression. In doing so, you're also going to remove your a term from your leading term. So in this case, step 1, we are going to turn 2x squared plus 5x plus 2 into x squared plus 5x plus 4. Now step 2, factor like normal. In this case, it's going to turn into x plus 1, x plus 4. Now the third term. This is a little bit weird. In the end, you're going to divide the polynomial by a, but you're going to do it a certain way. So what you're going to do is you're going to see your constant term in each of the polynomials, and then you're going to divide that by a. So in this case, it's going to be x plus 1 over 2 times x plus 2. You see what I did here? I divided this by 2, and I divided this by 2. Now, if you end up with a constant term involving a fraction, what you're going to do is you're going to multiply the entire term by its denominator. So you want to end up with a polynomial with no denominators. So in this case, the denominator is 2. I'm going to multiply the entire polynomial by the denominator, and I'll end up with 2x plus 1 times x plus 2. If I had, let's say, a x plus 7 over 3 term, and a x minus 1 over 2 term, what I would do is I would multiply this by 3 to get rid of the denominator, and multiply this by 2 to get rid of the denominator. So that would look like 3x plus 7 times 2x minus 1. So that is basically the process of doing it. Now looking at this, we end up with the final factorized version of our above expression. And let's go ahead and FOIL that out just to check that our method actually works. So we have 2x squared plus 4x plus x plus 2 equals 2x squared plus 5x plus 2. Does that match up with our first equation? It does, so our method works. And yeah, that is how you factor a quadratic expression with an a term not equal to 1. So there's actually another quadratic expression that you're also going to need to learn how to factor. It is called, it is called a difference of squares. So these take the form of something like x squared minus a squared, or a squared minus x squared. It's basically just like square minus square without the middle term. And if you want to factor these, simply break the polynomial into x plus a times x minus a. So these will come by memory. You can't really do anything to prepare for them other than just being able to recognize square minus square. So let's just say we have something like x squared minus 4. Let's factor this. So our leading term, x squared minus 4, our leading term, x squared, is going to be our first term. And we're going to have a plus, we're going to have a minus. What's the square root of 4? It's 2. So we put in a 2 here, put in a 2 here. Likewise, x squared minus 9 breaks into x plus 3 times x minus 3. Occasionally, the a squared term will be a number like 2. In this case, your constant term will simply just be square root 2. So if you think of your constant term, let's say x squared minus 2, if you think of this being, instead of 2, being square root 2 squared, then you can apply what we have done here into your polynomial. So this would break into x plus square root 2, x minus square root 2. This also works the other way, by the way. You can have 2 minus x squared, in which case you would have root 2 plus x and root 2 minus x. Essentially, the term with the negative coefficient is going to be the one that is added in minus. Okay. Sometimes your term is going to have two variables, or your polynomial is going to have two variables, sorry. They follow the same rules, but instead of numbers, you're using letters. So let's say x squared plus minus y squared. If we factor that, that's just going to become x plus y, x minus y. You want to multiply it in and check it? Go for it. We have x squared minus y squared plus yx minus yx. These two terms cancel, and we're left with x squared minus y squared. Again, this also works if you have y squared minus x squared. Let's factor this into y plus x, y minus x, and then if we were to FOIL that out, we would again get y squared minus x squared. It's good to memorize this identity just because it's going to appear so much, and it'll be really useful for you to be able to factor it on site. All right, before we finish, I'd like to sum up some things and also add on some tricks to factoring that I thought I'd mention. So number one, before you factor, add up your like terms. It just makes everything a lot easier and condenses the equation. So what do I mean by that? Let's just say I have x squared plus 3x plus 4x plus 5x squared plus 2x. Let's say I wanted to factor this, right? What I would do is I would add up all the like terms. So this would turn into 6x squared plus 9x. Then we can immediately see that the entire expression is going to be factorable by 3x, because 3 goes into 6 and 9, x goes into them both. So we get 3x times 2x plus 3. If you didn't combine like terms, I don't think you would have seen that. So it's really helpful to do. Just combine everything, it makes everything so much simpler. Number 2. Constants are your friend. If they're very easily recognizable, then that usually makes factoring everything else a lot easier. So let's just say we have numbers like 144y squared plus 132 x plus 68. And we wanted to factor this expression into a more condensed form. What we would do is we would just simply factor them constant by constant. So we know that everything here is going to be divisible by 2 because they end in even numbers. And now we can immediately factor out a 2. And we end up with 72y squared plus 66x. 66? Yeah, 66 plus 34. And then we can just do it again. So we'll factor out another 2. 36y squared plus 33x plus 17. And unfortunately, this can't be factored anymore, but we were able to, even though we didn't know that it was factorable by 4, we were able to figure it out by just factoring partially by 2's. And, you know, for some other numbers, you'll be able to do it by 3's, by 4's, by 5's. Gonna finish this up. Okay. Next. Another thing to quickly notice is the signs of the last term. So in a quadratic, there will be 4 formats. There will be something like x squared plus 5x plus 6, x squared minus 5x plus 6, x squared minus 1x plus 6, and x squared plus 1x minus 6. Oh, wait, sorry. This should be a minus as well. Okay. So if we look at the first one, this one's going to break into x plus 3, x plus 2. We look at the second one, it's going to break into x minus 3, x minus 2. Notice that the last term has a positive coefficient. This means that both of your constant terms in your factored polynomials, so in this case the 3 and the 2, are going to have the same sign. This is because if you have a negative 2, you have a negative 3, when they multiply, they make 6. And your last term is always going to be a multiple of your constants. So in this case, negative 3 times negative 2 equals 6. 3 times 2 equals 6. Now, in the below expressions, this is just going to be, you know that it's going to be one positive and one negative. If the n term is, if the, why is this not deleting? That is annoying. Okay, you know what, we're going to leave it. If the b term is negative, you know that the bigger number is going to be attached to the negative, and the smaller number is going to be the positive. Why? Because when you add them up, negative 3 plus 2, remember your constant terms added together make b. That's negative. If you have a bigger negative number added to a smaller positive number, you still end up with a negative. Same logic goes for here, except instead of being negative, it'll be positive. Your bigger number will be positive. That's because 3 minus 2 equals 1. There's your b term.